Hello and welcome back to another stats video. All right, so we're going to continue our exploration of probability. All right, so we're going to talk a little bit about sample spaces. We're going to talk a little bit about Venn diagrams and just go into some of the basics before we get into the more involved aspects. So probability model, what is it? Why do we care about it? It is a description of a chance process that contains two parts. So I know what you're asking yourself. What are those two parts? One is a list of all possible outcomes. So basically, with this chance process, what's possible? What could potentially happen? And then two, the probability that each outcome will occur. Okay, so a full probability model is a list of all the possible outcomes and the probability that each of those outcomes will exist. Now, this right here, this list of all possible outcomes, is what we generally refer to as the sample space. All right, so this is the set or list of all possible outcomes for a chance process. All right, so what we have here is a visual representation of a sample space. So if you were rolling two six-sided fair dice, which means each side is equally likely, this would be your sample space. This is all the possible outcomes that could arise from rolling two unique six-sided dice. All right, so you'll notice there's 36 choices in total, and since it's a fair die, we know that each of those is equally likely. So each of those outcomes has a 1 in 36 chance of happening. So when we're talking about the probability model is the combination of all the possible outcomes, aka the sample space, and the probability of those outcomes, which in this case would just be 1 out of 36 for all of the options. All right, so this question here says, how many outcomes are possible? Consider the dice as two separate colors. That is 1, 2 is different from 2, 1. We just answered that. There are 36 different possibilities. Are these outcomes equally likely? If yes, what is the probability that each will occur? So we answered that as well. Yes. And the probability that each one is going to occur is 1 out of 36. All right. So again, nothing there that's overly complicated, just getting familiar with these two terms so that if I ask for a probability model, you understand that you're listing out all the outcomes, which is called the sample space, and you're listing the probability that each of those outcomes will occur. So right here we say practice sample space. List out the sample space for flipping 3 coins. Similar to the dice, the coin should be thought of as numbered 1, 2, and 3, so that HTT is different from THT. Now, my only recommendation when you do something like this is just make sure you have like an organized way in your head of doing it, so that you don't accidentally miss any of the possibilities. So, for example, we could start with heads, heads, heads. And then I might say to myself, all right, well, I'm going to start just by flipping this last piece here. Heads, heads, tails. All right? And then I might say, all right, now I'm going to flip the middle piece. So heads, tails, heads. All right, now I'm going to flip the middle and the back piece. Heads, tails, tails. All right. Now I'm going to flip the front piece. Tails, heads, heads. All right, and now I'm going to repeat the process, but I'm going to have the tails as my leading part. So tails, heads, tails, just like I did on this line. Then I'm going to go tails, tails, head, just like I did on this line. And then eventually that's going to get me to tails, tails, tails. All right, so that would be the complete sample space here. And again, not hard to do. You just have to make sure that you're like methodical about it so you don't miss anything. Also, the number of possibilities, we can figure that out by flipping a coin. There's 2 possibilities, and we're flipping the coin 3 times. So that tells us in total there's going to be 8 possibilities. In the same way that up here, the die had 6 sides, and we were rolling it twice. So there's 36 possibilities. So if you remember that kind of rule, it's called the counting principle. You can make sure that your final sample space has the right number of things. And if you're like, oh, I'm supposed to have 8 and I only have 6, that tells you that you accidentally missed something. And you want to go back and just kind of figure out which one it was. And then this one doesn't ask, but to make it a full probability model, we could add that all sequences have a 1/8 chance of happening or occurring. All right. So again, nothing overly crazy here, just making sure that we've got some of this basic vocabulary down so when we use it later on, you know what we're talking about. Speaking of another piece of basic vocabulary, we have the event. All right. So the event is any collection of outcomes from some chance process. An event is a subset of the sample space and then last but not least, events are often designated with capital letters. All right, so here we have let A be the event, notice capital letter, rolling 2 dice and getting a sum of 5. So that's a subset of our entire sample space, right? It's a specific subset of this larger sample space that shows all of the combinations when rolling 2 dice. We're focusing in on that and saying, all right, what's the probability of rolling 2 dice and getting a sum of 5? That's our specific event that we're looking at. And then it says, what is the probability of A? So we could go back to here and say, all right, we're trying to look for the ones where they add up to 5. So that adds up to 5. That adds up to 5. This one adds up to 5. This one adds up to 5. And then nothing from either of these rows can add up to 5 because you've got 5s and 6s. So anything you add to those is going to make it too high. So in total, there are 4 ways that we can sum to 5. So the probability of A is 4 out of 36, which also reduces to 1/9. Now, we use dice a lot, so it can be helpful to kind of learn this sequence, but if you're talking about how many ways are there for the dice to add up to various sums, the possible sums go from 2 to 12, obviously 2 1s to 2 6s, so 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, 2, there's only one way to get a 2. You have to have double 1s. There's only one way to get a 12. You have to get double 6s. There are 2 ways to get a 3. You can either do 2 1 or 1 2. There are 2 ways to get an 11. You can either get 5 6 or 6 5. And what we're going to see is there's a pattern here that sort of repeats. So there's 1 out of 36 ways to get your 2. There's 2 out of 36 ways to get your 3. There are 3 out of 36 ways to get your 4. We already saw that there are 4 out of 36 ways to get your 5. 5 out of 36 ways to get a 6. 6 out of 36 ways to get a 7. And then it's not 7 out of 36 ways to get an 8. We start coming back down. So 5 out of 36 ways, 4 out of 36 ways, 3 out of 36 ways, 2 out of 36 ways, and 1 out of 36 ways. All right, so because we just deal with dice so often, they're just like a convenient mechanism when talking about probability, it's helpful to kind of remember this pattern and know that 7 is the most likely outcome, and there's 6, and then it just pyramids down from there. So if you can just remember that there's 6 ways to get a 7, 1 way to get a 2 or a 12, the rest can sort of kind of fill itself in for you. All right, so the second question says, let B the event, again, capital letter, rolling 2 dice and not getting a sum of 5. And then we have this notation here. What is the probability of B? I kind of glossed over that here, but this notation is basically saying, probability of B. Now, we could say to ourselves, all right, well, what's the probability of not getting a sum? Well, we could take this and say 1 plus 2 is 3, 6, skip this one because that's the one that we're trying to avoid, 11, 17, 22, 26, 29, 31, 32. All right, so the probability is 32 out of 36. That's getting a sum other than 5. And hopefully you didn't actually need to add that up. Hopefully you could say to yourself, well, if there's a 4 out of 36 chance of getting a 5, that means there's a 32 out of 36 chance of not getting a 5. All right, what do you notice about the probability of A and B? They sum to 1. Why is that significant? Because it implies that they are complements. All right, so the probability that an event does not occur all right, so the complement is the probability that an event does not occur. And similarly, we can always say that the probability of a complement of an event, and then we're just going to call that event E for right now, is 1 minus the probability of E. All right, so the complement is the probability that an event does not occur. And then the probability of that complement can always be found by just doing 1 minus the probability that the event occurs. All right, and I think that's pretty intuitive. But again, we're just putting a word on that and saying that those two things are complements. So let C be the event rolling a sum of 2. What is the probability of the complement of C? So this is saying the complement of C. All right, and what we're going to see is that sometimes it's easier to calculate the complement and then use the knowledge that they always add up to 1 than trying to calculate a probability directly. All right, there's going to be times when we try to find a probability directly and it's going to be really difficult. There's going to be a lot going on where the complement's going to be much, much easier. And then we can use this little rule here to find the probability of the event that we were actually interested in at the start. All right, so let C be the event rolling a sum of 2, which we know there's only one way of doing. So what's the probability of not rolling a 2? It's just 1 minus 1 over 36, or put another way, 35 out of 36. All right. What is the probability of not rolling doubles? All right. Again, this might be one where it's easier to find the probability of rolling doubles and say, okay, well, there's 1, 2, 3, 4, 5, 6 ways of rolling doubles. So the probability of doubles is 6 out of 36. So the probability of not doubles is 1 minus 6 over 36, or put another way, 30 over 36. Or put another way if you want to reduce that, 5 out of 6. All right, but it just kind of shows you that sometimes it's easier to calculate one thing and find the complement than necessarily calculating this directly. All right, so this idea of complements is just going to make our lives easier if you can sometimes recognize situations where, okay, this, might be useful, or this might be a shortcut to kind of arriving at the answer that I'm trying to get. What is the probability of rolling a sum of 3 or 4? All right. Well, we know the probability of 3 is 2 out of 36. We know the probability of 4 is 3 out of 36. So the probability of 3 or 4 is just going to be 5 out of 36, those two added together. So continuing on, mutually exclusive or disjointed events. All right, what does it mean for things to be mutually exclusive? All right, these are events that have no outcomes in common. So they can never occur together. All right. Now, you might not have realized it, or you might not have been thinking about it, or you might not have cared, maybe all of the above, but these two events here were mutually exclusive. All right. If I go back to my sample space, there's no overlap between a sum of 3 and a sum of 4, which is what allowed me to directly add these two probabilities. All right. Now, that might have just seemed like common sense, but there are rules of probability that are coming into play there and it deals with this idea of mutually exclusive. All right, when two events are mutually exclusive, you're able to just combine their probabilities. When they're not mutually exclusive, we're going to see that there's other things that we have to account for. So let's kind of go through this thought exercise here that focuses on a deck of cards. What is the probability that you randomly choose a queen from a standard deck of playing cards? So we're going to assume that's not including the jokers. So that means that there are 52 cards in total. So the probability of choosing a queen, there are 4 suits in a deck. So 4 out of 52, which reduces to 1 out of 13. All right, there are 13 different cards because you have the ace through the 10, and then you have jack, queen, king. So 13 different cards. All right, what is the probability that you randomly choose a king from a standard deck of playing cards? All right, same exact thing. There's still 4 kings, diamond, heart, spade, and club. So we're still looking at the same 4 out of 52 or 1 out of 13. What is the probability that you randomly choose a king or queen from a standard deck of playing cards? All right. And then the note says, since these events are mutually exclusive or disjoint, you can simply add the probabilities. So the odds of getting a king or a queen is 8 out of 52 or 2 out of 13. Now, how is the following question different? What is the probability of choosing a king or a spade from a standard deck of playing cards? All right. Well, what makes this different is there's overlap. All right, we have the king of spades that impacts both of those. All right, the king of spades is both a king and a spade. So when that's the case, we have to account for that and say, okay, well, there's 4 kings, there are 13 spades, but because of this overlap here, we've actually double counted the king of spades. We counted it once here, we counted it once here, so we have to subtract that overcount that we did to get the correct answer. Otherwise, we're double counting the king of spades. And then we end up with, 16 out of 52. All right, but the general idea here is that when you have overlap, instead of just being able to sum them, it's the probability of A plus the probability of B minus the probability of A and B. All right, and that's what this was doing right here. All right, we started with the probability of A, probability of a king, added the probability of spades, and then subtracted the overlap that kind of fits, that goes in there. So let's talk about some basic probability rules. Any probability is between 0 and 1. If you ever tell me that a probability is above 1 or below 0, I can tell you that you've gotten the question wrong. Events that are certain to occur have a probability of 1, while impossible events have a probability of 0. Right? So the probability of a correct answer being above 1 is 0. The probability of your answer being wrong, if it's above 1 or below 0, is 1. All right, so events that are certain to occur are 1, impossible events are 0. All possible outcomes together have probabilities whose sum is 1. So if you look at every single possibility, those probabilities have to sum to 1 because you've accounted for every option. So they have no choice but to sum to 1 because otherwise you're missing something. There's a scenario you haven't considered. 4, if all outcomes in a sample space are equally likely, the probability that an event occurs can be found using the formula number of outcomes corresponding to the event divided by total number of outcomes in the sample space. All right, that's what we were doing with the dice. We were saying, okay, there's 36 total choices. And since each of these is equally likely, we can just say, oh, there's 4 ways to get this, or there's 10 ways to get this, and just continually put it over 36 because everything was equally likely to have happened. The probability that an event does not occur is 1 minus the probability that it does occur. This was that whole complement idea that we just talked about. And then if 2 events have no outcomes in common, the probability that one or the other occurs is found by adding the individual probabilities. Again, having no events in common is another way of saying mutually exclusive or disjoint. All right, you can use either of those phrases there. All right, so moving on. Back to our two-way table. All right, we're going to be using these a little bit in this unit, especially when we talk about independence and conditional probability. So they are going to pop back up. So let's just go through one of these quickly. So it says when trying to find probabilities involving 2 events, a two-way table can display the sample space in a way that makes probability calculations easier. All right, so we have our two-way table here. First question says, what is the probability of having pierced ears? Okay, so there's that. We know there's 178 people in total, so the odds would be 103 out of 178. What is the probability of being male with pierced ears? All right. So we know that that one is referring to this box right here, being male with pierced ears. So we can say, oh, that's 19 out of 178. And you can just see that the two-way table structure just makes it very easy to access the individual pieces that you need in a quick and efficient manner. And then this last one says, what is the probability of being male or having pierced ears? So now we're looking at 2 different situations. We're looking at this one right here. That's the probability of being male. And we're looking at the probability of having pierced ears, which is these 2 right here. And this, I think, kind of visually highlights the double counting problem, is that 19 falls in both pieces. So there's 2 ways you can do this. You can either say, all right, well, male plus pierced ears is 103 plus 90, but then I'm going to subtract the 19 because I double counted that. Or you could just look at these 3 individual boxes and say, oh, okay, so it's 84 plus 19 plus 71. And the two-way table just kind of gives you a quick and easy way of seeing what that's going to be. All right, so both of these are going to work out to be 174. All right. The other way of looking at it is saying, well, there's only one box that we're not looking at. So we could say, what's the probability of being female without pierced ears? And then do sort of a complement situation. Either way, you're ending up at that same number. And again, this is a silly example, but as things get more involved, we're going to see that, sometimes it's easier to do it one of these 3 ways, as long as you end up in a place where you're saying 174 over 178, that's where you need to be at the end of the day. All right. So again, this just ties into that general addition rule that I just talked about. But let me just write it down here. If A and B are any 2 events resulting from a chance process, then the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. And what I want to note is this right here will be 0 when the events are mutually exclusive. All right, so if you have two events that are mutually exclusive, there's literally no way for these both to be true at the same time. And when something literally can't be true, when something's impossible, the probability is 0. So then it reduces to just the probability of A plus the probability of B. All right, it's only when there's that overlap that you have to worry about subtracting out the probability of A and B like we did here. All right. So sometimes it can be useful to kind of visualize these things and to make it a little more clear about what's happening. And basically the tool that we primarily use for that is these Venn diagrams. So, this is what we just were talking about here. Here's your event A. Here's your event B. So this is A, this is B, and then this right here is the overlap where stuff is being double counted. All right, so that's the part that we have to subtract away because there's an overlap there. So everything we just kind of talked about, can be represented via Venn diagrams. All right, this one right here is representing the complement situation. So if you're trying to visually represent a complement, you have the event, and then you have everything that's not the event. And together, that makes up all of the possibilities. Right? When there's no overlap between the circles, that's what we call mutually exclusive, because it's impossible for those two things to happen at the same time. All right? When we see this U here, that stands for union, and it basically means A or B. We're looking for the probability that either of those will happen. All right, when you see an upside down U, that's talking about the intersection, and that implies A and B. Both of them have to be true, or we're only looking at the situation where both of them are true. So again, just can be a useful tool here to sort of help visualize what's going on. All right, so that's where we're going to stop for today. Next time, we're going to look more at like conditional probabilities and independence and some of the different stuff we can do with that. But this is sort of a good stopping place for right now. So if you have any questions, feel free to reach out. Otherwise, have a great day.